Let's see axially loaded compressor members. Overall flexural overview of flexural buckling, we can see it. Flexural buckling is a critical consideration in the design of axially loaded compressor members. So flexural buckling is mostly coming in the problem of axially loaded compressor members only, especially when assessing the stability under load. This phenomenon can be categorized into two primary types. One is inelastic buckling, another one is elastic buckling. We can see each governed by specific slenderness ratios and material properties. It's all depends whether it's going to be inelastic buckling or elastic buckling. It depends on the slenderness ratios and material properties. Inelastic buckling occurs when slenderness ratio KL by R. This KL by R is the slenderness ratio that we know. If this inelastic buckling occurs if it is less than 4.71 times square root of E by Fi. If the slenderness ratio, when we calculate, if this value is less than this 4.71 times square root of E by Fi, then inelastic buckling occurs. So when do the elastic buckling occurs? Elastic buckling occurs if this ratio, for accurate analysis, it's crucial that if KL by R ratio is greater than 4.71, then elastic buckling occurs. Okay. And also the ratio of Fy by Fe is less than or equal to 0.25, inelastic buckling occurs. In this regime, material behavior transitions from elastic to inelastic, significantly affecting the member stability. Critical stress calculation. We can see how to calculate the critical stress. The governing equation in this scenario is FCR equal to critical stress is 0.65 times 658 power K. 0.658 power K into Fy, yield value. K is nothing but Fy divided by Fe. Fy is the yield stress, Fe is the elastic critical buckling stress, that we can calculate pi squared E by KL by R squared. KL by R we can say lambda, so pi squared E by lambda squared. That's the elastic critical buckling stress. FCR is the critical stress, Fe is elastic buckling stress. Critical elastic buckling stress. This is critical stress, this is elastic critical buckling stress. For accurate analysis, it's crucial that Fe is greater than or equal to Fy by 2.25. This ensures that buckling behavior can be effectively modeled using inelastic assumptions, which are more conservative and safer for design. Next, we will see the elastic buckling. This elastic buckling is relevant when the slenderness ratio KL by R exceeds 4.71 square root of E by Phi and ratio Fy by Phi is greater than 2.25. In this case, buckling behavior is dominated by elastic response of the material. Critical stress in this calculation is FCR equal to 0.877 Fe. That is number K and R. This equation illustrates that critical stress is percentage of the elastic critical buckling stress. So 87 percentage is the 87.7 percentage of elastic critical buckling stress will be the critical stress, indicating that the structure is still within the elastic limits. Transition between inelastic and elastic buckling. The transition point between inelastic and elastic buckling behavior is critical threshold that influences the design approach. This point is summarized in this table, which deals with the limiting slenderness ratio. Here you can see limiting slenderness ratio for yield value, and elastic critical stress also we can calculate in this way. Here we can see nominal compressive strength. Nominal compressive strength is FCR into Ag, cross area of the member Ag. FCR is the critical stress. Design an allowable compressive strength. To ensure safety and reliability in the design, both design compressive strength and allowable compressive strength must be calculated. Design compressive strength, we can say phi c into Pn. Design compressive strength, it should be greater than or equal to Pu, ultimate load resistance factor design. Pu represents the required compressive strength based on this one. Allowable strength is Pn divided by safety factor. Phi c is resistance factor, and phi c gamma c. Allowable compressive strength should be greater than or equal to Pa. Pa is the required compressive strength based on allowable stress design. Phi c is the precedence factor for compression. Lambda c is the 1.61 safety factor for compression. Here we can see what is defined axially loaded compressed member. A structural element subjected to axial loads that compresses the member along its length is called compression member. How does the slenderness ratio affect buckling? A higher slenderness ratio increases the ratio of likelihood of buckling under axial load. Higher slenderness ratio increases the likelihood of the buckling under axial load. What distinguishes between elastic and inelastic buckling? Inelastic buckling occurs at a lower slenderness ratio. If slenderness ratio is low, then inelastic buckling happens, whereas where material yields, while elastic buckling occurs at higher ratios of slender before yielding. How is the critical stress calculated in elastic buckling? FCR equal to 0.658 power K into Fy. K is Fy by Fa. What conditions indicate inelastic buckling? If K by I is less than or equal to 4.7 into square root of Fy and Fy by F is less than or equal to 2.25. What is the role of yield stress in buckling? It determines the point at which material begins to yield and influence buckling capacity. How is elastic critical buckling is derived? Calculated as pi square by KL by R square. What happens if slenderness ratio exceeds the limit or limits are exceeded? That means like member is more prone to elastic buckling, reducing its load carrying capacity. How does AIC 360 guide comparison by design? It provides equation criteria for calculating strength and stability of members. What equations govern critical stress for elastic buckling? FCR equal to 0.877 Fe, that is for the elastic buckling prevails. Condition where elastic buckling prevails. How do material properties influence buckling behavior? They determine yield stress, modulus of elasticity, and overall stability. What factors determine the gross area, members cross-sectional dimensions, and shape? How is nominal compressive strength calculated? That is FCR in dA by AG is the gross area. What is the element of resistance factor? It accounts for uncertainties in material strength and ensures safety in design. It considers or accounts for uncertain materials. How do LRF AST differ in strength design? LRF uses load factors and resistance factors. AID uses safety factor applied to allowable stress. What is the relation between the design and required compression? Design strength must meet or exceed the required strength. It provides critical stress values for various steels and facilitating quick reference. What safety factors are used in compressive strength calculations? The commonly phi c is 0.9 for LRD, gamma c is 1.67 for AST. How can slenderness ratio assessments be verified? By calculating KL by R using accurate dimensions and material properties. What are the common applications of compression member? Column, brace, structural frames, and buildings. Let's see an inelastic buckling example. Fo is 36 KSI, X modulus, effective length factor, length, radius of garrison. So first step, calculate slenderness ratio. Okay, second step, Fe. We can get pi square by KL by R squared. We can get each term. So calculate Fe 110. Calculate K value. K value is Fo by Fe 0.326. Then FCR we can calculate 0.658 power 0.326 and 36. It becomes 0.813, so 0.813 of 36. So it becomes 81% of FOI value. So we can see elastic buckling calculation, yield value, X modulus, K value, length, radius of garrison. So KL by R we can calculate, Fe also we can calculate 110, and Fy by Fe is 0.453. FCR is equal to how much? 76% of yield value. So this is inelastic buckling and elastic buckling. So alright, today we are diving into the topic of critical buckling stress. It's essential for understanding how our columns will perform under load. What are your thoughts on the formulas we use? I think the formula FCR equal to 0.68 per K is a straightforward. It shows how yield strength plays a crucial role. Have you both checked it how to calculate K? Yes, K equal to F by Fe, right? But what's important is how we determine Fe. So Fe is calculated using By studying weak bear spread, the effect on the candidate is various key variables influence buckling behavior. Right, and find it interesting how sluggishness ratio affects the whether we use inelastic or elastic form buckling equations. We need to ensure that we are applying correct conditions. So if you have a high sluggishness ratio, we typically see the elastic buckling taking precedence, right? Yeah, correct. When KLBR exceeds certain limits, we switch to elastic buckling formula. Understanding this transition is crucial for accurate design. Agreed. We should also consider material properties. Different steels have different yield strengths, which will impact our calculations significantly. And what about safety factors? How do we incorporate those into our design? Good question. We often apply resistance factor when we calculate the design strength, and we account for uncertain material properties and loading conditions. It's also worth noting that how critical buckling stress ties to overall structural stability. A failure in buckling load can lead to catastrophic consequences. So what do we do if you find our calculated FCR is lower than expected? So we may need to revise our design. This could mean that increasing column size, changing the material, modifying the effective length to enhance stability. It's definitely a balancing act. Designing for strengths while considering cost and weight. It sounds like continuous evaluation is the key throughout the design process. That's right, exactly. Always check assumptions. Don't hesitate to reach out for peer review if you are unsure. Collaboration can catch issues early. Let's wrap this up. How would each prepare a quick summary or critical buckling stress for next meeting? Sounds like a plan. I'll focus on the implications of sluggishness ratio in my summary. Great idea. I'll tackle the calculations of FCR, how to apply in real world scenarios. I'll look into different material properties and how they affect the buckling. Let's meet again tomorrow to share our findings. Looking forward to it.